Have you ever heard stories of strange, eerie lights appearing in the sky just moments before a powerful earthquake? Flickering glows, colorful flashes, or even beams shooting up from the ground. For centuries, these accounts were dismissed as myths, hallucinations, or simply misidentified phenomena like lightning or power line flashes. But what if these mysterious lights are real? What if they are a genuine, albeit rare, warning sign from the Earth itself? Today, we're diving deep into the fascinating and once baffling world of earthquake lights, or EQL, and uncovering the scientific explanations that are finally bringing this mystery out of the shadows. So, what exactly do these lights look like? The descriptions are incredibly varied. People have reported seeing everything from small, floating globes of light, similar to ball lightning, to large, sheet-like flashes that illuminate the entire horizon. They've been seen in a rainbow of colors: blue, white, green, and even multicolored displays. Some appear for just a split second, while others linger for several minutes. They can emerge directly from the ground, hover in the air, or seem to come from high up in the atmosphere. The 2017 earthquake in Mexico City gave us some of the clearest video evidence to date, showing the night sky erupting in pulsing flashes of green and blue light as the ground began to shake. It was a stunning and terrifying sight that left scientists and the public demanding answers. For a long time, the scientific community was skeptical. Without consistent, reliable data, it was easy to attribute these sightings to other, more common events. Power lines snapping and arcing during a quake can create bright flashes. The stress on power transformers can cause them to explode. Even meteors or distant lightning could be mistaken for something more mysterious in a moment of panic. These are all valid explanations for some sightings, but they don't account for all of them. For instance, they don't explain lights that appear in remote areas with no electrical infrastructure, or lights that are seen minutes or even days before the earthquake actually strikes. The sheer volume of credible reports, stretching back to ancient Greece, suggested that something more profound was at play. The turning point in understanding earthquake lights came with the realization that they are most often associated with specific geological conditions. EQL are not seen with every earthquake. Instead, they seem to prefer areas with vertical or near-vertical fault lines, known as rifts. Unlike the more common subduction zones, where one tectonic plate slides under another, these rift environments allow for a unique electrical process to occur deep within the Earth's crust. This is where the leading theory, the positive hole theory, comes into play. It sounds like something out of science fiction, but it's grounded in solid physics. Let's break it down. Deep within the Earth, rocks are under immense pressure. This constant stress can break the chemical bonds within the mineral crystals of the rock. Specifically, it can break the peroxide bonds in oxygen-rich minerals like quartz and feldspar. When these bonds snap, they release pairs of negatively charged electrons. However, for every electron that is freed, a corresponding positive hole, or p-hole, is left behind. Think of it as a mobile spot with a positive charge. While the electrons themselves are often trapped, these positive holes are surprisingly mobile. They can flow through the rock, almost like a current. Under the extreme stress leading up to an earthquake, vast numbers of these positive holes are generated. They begin to surge upwards from the depths, traveling through the rock strata towards the surface. They move at incredible speeds, sometimes as fast as 200 meters per second. As this massive wave of positive charge reaches the ground, it builds up an incredibly strong localized electric field at the surface. This is the key. This powerful electric field is strong enough to ionize the air molecules just above the ground. And what happens when you ionize air? You create a plasma, and that plasma emits light. This is the very same principle behind neon signs or the auroras. The type of gas molecules in the air determines the color of the light. For example, ionized nitrogen might produce blue light, while ionized oxygen could produce green or red light. This theory beautifully explains the variety of colors recorded in earthquake lights. It also explains why they often seem to be coming directly from the ground or hovering just above it. The light is literally being generated by the air at the surface, becoming a glowing plasma. This positive hole model, developed by physicist Friedman Freund and his team at NASA, successfully explains many of the puzzling aspects of EQL. It explains why they are linked to specific types of faults. The vertical structures of rift zones act like perfect conduits for these charge carriers to race to the surface. It explains why the lights can appear before the main shock, as the stress buildup and rock fracturing begins well before the final rupture. And it explains why they can take on so many different forms, from steady glows to rapid flashes, depending on how the charge is released at the surface. So, if this phenomenon is real, and we're beginning to understand it, can we use it to predict earthquakes? This is the million-dollar question, and the answer is, not yet, but maybe one day. The biggest challenge is that earthquake lights are a rare and inconsistent precursor. They don't happen before every quake, or even most of them. We still don't fully understand all the conditions required to produce them. However, researchers are actively working on this. They're setting up magnetometers and other sensors in seismically active rift zones, like the Rhine Valley in Europe or the St. Lawrence River Valley in Quebec, Canada. The goal is to detect the huge magnetic and electrical field changes that should, in theory, accompany the surge of positive holes to the surface. If we could reliably detect these pre-earthquake electrical signals, it could become a vital component of a multifaceted earthquake early warning system. It wouldn't be a single silver bullet for prediction, but it could provide a crucial piece of the puzzle, alongside other precursors like ground deformation, radon gas release, and foreshocks. Imagine a network of sensors that could detect these telltale electrical signatures, potentially giving a warning minutes or even hours before a major quake. That's enough time to stop trains, shut down gas lines, and for people to get to a safer location. It's a future worth striving for. Beyond the positive hole theory, other mechanisms might also contribute to the phenomenon. One is the piezoelectric effect, where certain crystals, like quartz, generate an electric voltage when squeezed. The immense pressure before a quake could squeeze quartz-rich rocks, generating huge electric fields. Another idea is triboluminescence, which is light produced from friction. The grinding of massive rock faces against each other along a fault line could theoretically generate light, although it's difficult to explain how this light would be visible at the surface. While the positive hole theory is the most comprehensive, it's likely that a combination of these effects could be at play, creating the diverse and complex light shows that have been witnessed. So the next time you hear a story about strange lights in the sky before an earthquake, don't be so quick to dismiss it. What was once considered folklore is now at the forefront of geophysical research. These ethereal glows are a powerful reminder of the immense and mysterious forces at work beneath our feet. They are a direct, visible manifestation of the incredible stress and energy being released from the Earth's crust. We are finally beginning to understand the language of our planet, translating its strange light shows into the language of physics. And in doing so, we might one day unlock the ability to hear its warnings before disaster strikes. Thank you so much for joining me on this journey into the world of earthquake lights. If you found this as fascinating as I do, please hit that like button and subscribe for more deep dives into the mysteries of our world. And don't forget to share your thoughts in the comments below. Have you ever seen or heard about earthquake lights in your area? Let's discuss. Thanks for watching.